Good morning. Good morning. Let it quiet down. My name is Jim Pappas. I am the Vice Chairman of SNIA, and thank you for coming here this morning. I work for Intel Corporation, and I've been involved with SNIA for the last 3.5 years. This is our fourth of these summits that we're doing. Every one of them has been very, very full in the room. The room holds about 250. We actually have 608 people registered for the event today, and not all of them will be here all day. And it's a free event, so we don't expect everyone necessarily to show up. But we do have a video overflow room upstairs, so during the day, you guys got here early enough to claim a seat. You may want to guard that. I'm sure it's going to be better to be in here than to be upstairs. The other thing is that because it's going to be a very full crowd over the day, please be respectful of, don't grab extra seats and stuff like that. Realize that people are going to be looking for seats, and there will be an overflow area. So I don't know if anyone's up in the overflow room right now, but we'll talk a little bit about that in a minute. So as I said, I work for Intel Corporation. If you need to get a hold of me, I'm pretty easy, jim@intel.com. And this is, I think, the most exciting thing that's happening in computer architecture, and I love to be up here and discuss this and talk about it. Today there's two things going on. This is part of a week-long summit symposium that Intel has. I'm sorry. No, I was up to 2. I was downstairs this morning at 6 a.m. exercising. I guess I didn't get enough sleep. This is the all-week symposium that SNIA is running. And today there's actually, after the keynote, after my introduction, Rick Coulson will be coming up and giving our opening keynote. And then the people in the symposium will be leaving and going to their meetings, and the summit will continue here. So for the rest of the day, this symposium and the summit will coexist and go forward. So this is the agenda for the day for everything. Including this evening, we have an evening reception, and we do our annual awards at that reception, so you feel free to stay and participate in that. SNIA at a glance. So, what is SNIA? From my perspective, SNIA has turned into one of the most important industry organizations, period. Up in the very, very top tier. And it's a lot of it is because of this work that's going on that we're going to talk about today. This is probably the most fundamental shift in computer architecture that is happening. It will affect every single person in this room, every single company that's represented in this room will be changed. The storage industry and the computer industry and computer architecture in general is changing in probably the most significant ways over the next several years as these types of technologies roll out. So we currently have 166 unique member companies, and it's a multinational organization. So we, across multiple geographies, we have offices in Brazil, in Japan, in EMEA, India, Southeast Asia, and of course North America. So it's a very, very broad organization. And of that, there's 3,500 active members. Most of them are volunteers. We have some paid staff, but we have mostly volunteers, and that comes out to over 20 members per company on average. That's a pretty big commitment, and that wouldn't be happening if this wasn't so much work going on. We reach about 50,000 end users per year through our various programs. And then on the right-hand side of the slide here, we list the types of programs we have that range from, just pure computer architecture and technology development, moving up through education and training for, the IT industries, and into conformance and interoperability types of programs. So it's a very, very broad organization. We have headquarters in Colorado Springs. We have a data center as part of that. We do some of our testing with. So from a organization standpoint, it's a very rich, very broad, and yet at the same time, as you see today, a very, very focused organization. So I think those are all attributes that make SNIA particularly strong. We have 2 events that we run a year, 2 large events, or large-ish events. There's 2. One in the spring is for end users. The one in the fall is for developers. So the next one coming up is the one this spring. It'll be held in San Mateo. And this is very much end user focused content. It's for people who deploy and manage and buy and in IT type of environments, and they come for training on SNIA technologies. And then after our flagship event is in the spring, a developer, I think anyone who would come to this is most likely a developer focused. And this is, many people have come to me and my peers on the SNIA board and said that this is the best technical conference that they attend all year. And see Mr. S.W. Worth from Microsoft is sitting there. He's the one who is probably responsible more than anyone for pulling together all that great content. Call for presentations will open next month. So love to have you participating. Today's summit is co-sponsored by, or underwritten by my company, Intel, and also by the Solid State Storage Initiative, which is one of the most active parts inside of SNIA. I have a slide for that next. Jim Ryan, here on my left, is the chair of that. He took over earlier this year after Paul Wassenberg from Marvell ran that for many, many years. He did a fantastic job, and Jim's come in and been trying to fill big shoes here, and I think doing a pretty good job. So I'd like to thank both SSSI and I guess myself for underwriting this conference. I heard Marty say that's so bad. The Solid State Storage Initiative is it's got a very clear mission. It's really really everything that has to do with anything solid state storage. So the whole SSD industry, moving them forward. They're responsible for the training and education and really driving the awareness and programs and testing and everything else for SSDs. And they're also responsible for the education of this, the content in this NVM summit. The number of focus areas, there's 2 I'd like to highlight. One is the NVDIM special interest group. If you go out when you get your snacks or later for food, there's a bunch of demos around, and there are, I think, 4 or 5 demos out there, and they're all NVDIM companies. And NVDIMs are the first extensions of this persistent memory, or this taking storage and memory and combining them into a single element on the computer. The other is the NVM programming model twig. I guess my oval got shifted here. Maybe it was moving from a Mac to a PC or something. I'm not sure. But the oval should be down. Those 2 are really the focus areas of today. There's the agenda. I'm not going to go through. We have a powerhouse agenda today with great speakers from across the industry. And I'll let that roll out today. As the day goes by, I'll be emceeing. If there's anybody up in the overflow room right now, we have a video feed going up there, but we don't have a reverse channel. So we're asking people to tweet to this address, and someone in the room will be able to take that for we can get questions from upstairs. I think most of you right now are probably sitting here as we talk. We do expect it to overflow to the upstairs at some point during the day. The afternoon session as well, there's some great stuff. Neil Christensen and Tom Tapley from Microsoft will be, I think, excellent speakers in this area and talk about what's going on in the operating system environment. And we also have Red Hat also talking about what's going on in the Linux environment today. So some really great stuff. We have some end user stuff, and I think you're going to be delighted. The special thanks, I'd like this, everyone who pulled this together. It's a lot of work for the whole symposium and for the summit. I'd like to personally thank Jim for taking the AR and leading this effort. All the attendees, the speakers that took time out of their busy schedule, and we already talked about the underwriters. So this is my last slide. I'd like to spend a few minutes here. When we started this effort on June 12th of 2012, it's a date that I had the honor of making the proposal that we pulled together the NVM programming twig. The idea is that there's a number of competing technologies that are all trying to have something that enters this bottom range here. Oops, sorry, wrong pointer. This bottom range here, this what I call the NUMA range, or Doug Voigt if he's in the room. This slide was originated by Doug from HPE. Excuse me. The idea is if you look at moving from hard drives to SSDs, moving from SSDs to NVMe SSDs, they're all significantly outside of what could be considered a normal NUMA range, off by at least 2 orders of magnitude, and in the case of hard drives by 5 orders of magnitude. This is a log scale, by the way, so things look like there's not that big of a difference, but it's massive changes between the lengths of those lines. On my screen here, that this is probably about a foot high. If you call it a foot, what is the relative height? Why do we compress it onto a log scale? Well, this one here is almost as tall as the Empire State Building. This one here is taller than the SATA SSDs are taller than any structure that'll probably ever be built by humans. For no other reason, you have to pressurize the building because those on the top would be subject to hypoxia, contamination. And then after the hard drives, if on a linear scale, would be well into outer space. Outer space is it's kind of nebulous because it's not a particular point where you're in the atmosphere and then not in the atmosphere. It's continually getting thinner as you move farther away from the planet. But a commonly used in the aerospace industry is the Kármán line, and the Kármán line is where for convenience sake, it's are you in the atmosphere or are you in outer space? And if you were in NASA and an astronaut, when you do your first mission and you exceed the Kármán line is when you get your astronaut pin, where you really become an astronaut. And this line here, oops, let's get it. This line here is the upper 2/3 of it are beyond the Kármán line. So if you put this on a linear scale, it puts it. You see why the ceiling just wasn't big enough in this room to handle this. Another way of thinking about this is the way I like to think about it is, and I got this from Gary Ornstein from Fusion.io several years ago, and smart guy, and so I stole it from Gary, and Gary stole it from some graduate student, I think at Champaign-Urbana. So, but the problem is that humans, all of us, it's very, very difficult for us to determine the difference between, nanoseconds, microseconds, and milliseconds. They're all kind of this infinitesimal kind of particles or whatever, time periods, and we just can't feel the difference. But there is, obviously, as engineers, most of us probably, we know that there is a difference, but we just don't feel it. So Gary's approach was, let's slow down the computer by a few billion X. And we're down to a clock rate of 1 per second. And furthermore, let's make this into a human computer. You know, you're the computer. So every time your heart beats, that's your clock. So every time your heart beats, you can get a piece of data. So if it's DRAM, every time your clock beats, you could read or write a piece of data. Whether you need to or not, that's the rate you can do it. And then, so what does it take to get to your SSD? Well, it's 3 orders of magnitude slower, so it's 1,000 heartbeats. It's 16 or 17 minutes. Walk a mile, you get a piece of data. Walk another mile and get a piece of data, another piece of data. This is that SSD that you know and you love, and it's your dearest thing in your life, and it's changed computing for you, and it's still like, compared to a human heartbeat, it's like getting data, it's like walking a mile. And this hard drive, that is like walking 1,000 miles, or I'll give you some mechanical advantage. I'll give you a bicycle, so you can bicycle 3,000 miles, get on in Seattle, get off in Miami, and you get a piece of data. And then turn around if you want the next piece of data. And that's the magnitude of what we've been dealing with in computer architecture. Everything in computer architecture is really designed, Van Neumann architecture is really designed for the fact that you have very slow, persistent memory, and you have very, very fast compute and local memory. So how do you, so when we looked at this and we saw what happened, well, clearly SSDs won't ever get you there. They have to get, 100 times faster. NAND's not going to get 100 times faster. But there was, at least a dozen competing technologies about, memristor and phase change and, spin torque and carbon nanotubes and on and on and on. So there's about a dozen competing things and variations of those things. And we recognize that if all it takes is one, if at least one of these succeed, then we get down into this NUMA range. And then there's only one logical choice that you can make, and that's that computer architecture is going to change. It's inevitable. It has to change. So it's too big of a change not to. So 3.5 years ago, we got in front of this. Andy Rudolph is sitting over here. He's oftentimes credited as the mastermind architect behind all of this. He's spoken all of these in the past, and this year his boss is going to do it. And Andy gets his first time sitting out and observing the conference. So so that was the idea. So if at least one of these technologies in this area succeed, then we could very, very reliably predict that a change is going to happen that will affect us all. So to talk about that, the first public announcements of this, or some of the first public announcements, is Intel and Micron's 3D XPoint. So it's my pleasure to invite Rick Coulson up. Rick is a senior fellow at Intel Corporation. I've worked with Rick for a couple of decades now, and one of the smartest guys I know. So here's Rick.
Okay, get the right one up.
There's at least 10 seats or so up here in front. Some of the back ones down.
Okay, which one did you want? The one that's up. Oh, no, okay. This one that says 2016 SNIA.
Oh, that one?
That one.
Okay.
There's nothing. Yeah, well, Jim was talking about the Carmen line. Carmen? Yeah, it made me think, based on the average age of the audience and everything like that, we all spent a fair amount of time basing our work on hard drives, which is up there. So I think we're all retired astronauts because we've been up there in the above that line in terms of latency, and now we're below. But actually, in this case, below is more exciting than above. So thanks for inviting me, everybody. I'm excited to be here. I just want to talk about how 3D XPoint, as an example of a storage class memory and one that we plan to ship this year in the form of SSDs and DIMMs, reinforces everything Jim said. System architecture changes. In fact, a lot of system architecture from Intel's point of view, has already changed in anticipation of this, but there's still a ton of work to do. And the main thing I want to leave you with is you'll see that the stuff that this is about, persistent memory, is the big payoff change. There are other things we're doing, and they're going to be great, but the big payoff is in persistent memory, and you'll see that. And that's really what I want to show. And I'm going to use 3D XPoint as an example. I'm not trying to be commercial about this or anything. I know the numbers, and so I can put them on charts and things like that about how it impacts performance and things like that. So please excuse if I say it too much. So I want to start with the latency journey. You know, we've been on this latency journey from up in this in the outer space in terms of latency, and we're coming down. And there have been a number of things along the way, and I want to set a little history context for that. And then I want to talk about the next step really being enabled by storage class memory, and 3D XPoint's an example. I want to talk a little bit about what 3D XPoint is, although I'm not going to say anything new that hasn't been said publicly. And then talk about the system and software architecture changes in place that are going on now. First, block storage. I'm going to talk about block storage quite a bit because the rest of the conference is not about block storage. And secondly, because it motivates the need for persistent memory. You'll see when we talk about block storage that the only way around some of the issues I'll talk about is persistent memory. Okay? Do we have time, Jim? Can you tell me when I've got like 5 minutes? Yeah, 1956, I know. It depends where you look. Which, interestingly, is the same thing. I'm the same age as the hard drive. Yeah. The RAM-Mac 350. I really want to focus on the latency, which is 600 and some milliseconds as 1.5 random IOPS. It is always interesting to look 5 megabytes and $57,000 and $15,200 per megabyte in 1956, $57. So come a long way, but I want to focus on the latency part of this. And that's way out there. I mean, that's like past the moon. You know? So, you know, we've been on this drive, we're on this journey for lower latency and storage, and that journey has not been a smooth one, meaning there have been some real discontinuities, is my point. You know, to a good 10K RPM hard drive, and I'm using like nice round numbers to make the math easy, that's only for 50 years, until about, you know, the 2008 maybe. That was the best you could do, and it was about 100x faster, only 100x faster in 50-some years. And then the advent of the modern SSD, performance SSD, that's another 100x, 60 microseconds, again, nice round numbers to make the math nice and even. 10,000x, another 100x, okay? But if you stop at the 10,000x, or two steps of 100x faster in latency in 58 years, what has CPUs done at the same time? Well, 100 megahertz best case clock. I put clock in quotations. It was kind of an interesting machine. But you know, today, and this slide is a little bit old, but again, to make the math work nicely, let's call it 3 gigahertz per core. So 30 million x. Okay, and that's pretty conservative because, you know, you got tons of cores and you got tons of sockets in a machine. So even though we've had the advent of SSDs reducing latency 10,000x, the other part of the system, if you will, is still 3,000 times faster than that. Now, there's nothing magic at all about that ratio. I mean, just happened to have this ratio back then. There's no science behind that. But it is interesting that there are still apps that with SSDs are bound by storage. And so the need for faster storage is definitely there. Not all apps, I mean, and certainly not apps that haven't changed. But there are a number of things that go faster when you have faster storage. Okay, so we're on this journey to drive latency down. And you know, we've got 100x here, 100x here. I put in NVMe SSDs separately from SSDs on SAS or SATA for one reason, and that is because there's been a pretty significant infrastructure change going from those buses to something that was designed with low latency storage. In fact, with storage class memory in mind, NVMe. And so, although the absolute latency with the same media isn't that different, and I'll get into details on this, the infrastructure is so that when you drop the media latency, that you can get a big effective gain in latency. And then, of course, then we move to this era of either persistent memory or very, very fast SSDs. And basically what I'm going to do now is go into some of the details about this infrastructure change, why with that infrastructure change, there's still, even if you have these ultra-fast SSDs, you still need persistent memory. Okay? Because, although the media bottlenecks are going away, you're getting more platform and software things in the way to get lower. Okay, so this is just a little bit, this section about 3D XPoint, what it is. I'll do this and I'll show a little video, and then I'll just use it as an example of how it fits in the storage stack and what happens. Most of you know this, but some of you probably don't. And this is not, the attributes may or may not be unique to 3D XPoint, but it's a XPoint structure, obviously from the name, which means you just have two wires crossing with some material in between, no transistors. The part about no transistors is really nice because it makes it really easy to stack. And so you can stack this. So for every 3 lines of metal, you get 2 layers of this memory. Because it's XPoint, it's the smallest feature size possible. It's a 4F squared or 4 lambda squared cell. The big breakthrough is, of course, what are these materials? What's the memory element and what is the selector element? And they have to be compatible with the other semiconductor processing. And then, of course, you want something that's very fast. And this particular memory is at the array level, not at the cell level. At the array level, it's about 1,000 times faster than NAND, roughly. Okay, so here's the video. This is short, but it does show some nice diagrams about the selection and stuff like that, so it's worth a couple minutes. No. Thank you, Jim. Let's see, how do we stop this?
Yeah, let's see if we got the audio turned off or something. No, where's this audio? There it is, muted. That's
Okay.
why. Okay, you want to start your video again?
Okay, let's start the video.
Yeah.
How would your life change if things could happen hundreds of times faster? If the wait went away? Maybe you'd have lunch in Paris, see a show on Broadway, have dinner in Beijing, and still be back in your own bed by 11. What if your storage device were that much faster? You could unleash the power of your processor instead of it working at a fraction of its potential like today. Eliminating that bottleneck requires better storage memory that is fast, inexpensive, and non-volatile, so your data doesn't go away when your power does. DRAM memory is great because it's very fast, but it's also very expensive and it's volatile. And unlike many silicon components, DRAM density isn't doubling every 2 years, so it's hitting a wall. On the other hand, NAND memory found in today's SSDs is both inexpensive and non-volatile. And while it's lightning fast compared to other storage technologies, up to 1,300 times faster than hard drives, it's still about 1,500 times slower than DRAM. But get ready, we're about to shatter today's rules in a very big way, thanks to some breakthrough engineering we've been working on. Soon, for the first time ever, we'll be able to equip computers with memory that's fast and inexpensive and non-volatile. Intel engineers have helped design a next-generation non-volatile memory called 3D XPoint, something many experts said was impossible. And this new technology isn't just twice as fast or even 10 times faster than NAND. It's up to 1,000 times faster. So how'd we do it? To make 3D XPoint inexpensive, we needed to pack lots of capacity into a tiny footprint. We started by slicing submicroscopic layers of materials into columns, each containing a memory cell and selector. Then, we connected those columns using an innovative cross-point structure consisting of perpendicular wires that enables memory cells to be individually addressed by selecting one wire on top and another at the bottom. We can stack these memory grids three-dimensionally to maximize density. And whereas DRAM requires a transistor at each memory cell to access or modify the cell, making DRAM big and expensive, each 3D crosspoint memory cell can be written to or read by simply varying the voltage sent to its selector, completely eliminating the need for transistors. This simple, stackable, transistorless design enables 3D crosspoint to pack up to 10 times more capacity than DRAM in the same space, greatly reducing cost. When it comes to memory performance, low latency is the key. Whereas NAND latency is measured in tens of microseconds, 3D crosspoint technology's latency is measured in tens of nanoseconds, a tiny fraction of NAND's wait time. This makes 3D crosspoint ideal for high-performance SSD storage, delivering up to 10 times the performance of NAND across a PCIe NVMe interface. Plus, 3D crosspoint technology's lifespan is not significantly impacted by how many write cycles it can endure, which means it can simultaneously serve as a single, high-speed, high-capacity pool of system and storage memory. There you have it, a truly disruptive memory technology that's fast, inexpensive, and non-volatile. Get ready to unleash your processor's true potential and realize possibilities we thought were decades away. So be sure to stay tuned for upcoming announcements on 3D crosspoint technology.
Okay, sorry about the fluffy, yeah, some of that's pretty fluffy, but like everybody likes the 9 equals 10, 10 times faster, 9 boxes. Intel does that like for our bonuses too. Like they talk about what the bonus is and then they have boxes and the boxes don't add up to the numbers. But anyway. I do like because it showed some aspects that I like. Anyway, so that's 3D crosspoint technology. Now, we're going to, some things changed on the fonts, but anyway, we're delivering both SSDs and DIMMs with this. I want to explain what Optane means. 3D crosspoint's the name of the memory, the brand of the memory developed with Micron. So 3D crosspoint just means this type of memory. From Intel or Micron. Optane means with the controller in a system level from Intel. That's all that is. I'm only explaining that to avoid confusion. So you'll see these called Optane SSDs and Optane DIMMs. So now, because people have talked about storage class memories for a long time, at last IDF we want to say, well, we're serious when we say this is real. So we wanted to show a demo of an early prototype SSD. And we did, and I don't have it here because it's a side-by-side demo and takes a little work to set up and all. But so we put together this little demo, just say QDEP1. That's a nice QDEP because it shows latency. So we read, so we have our best NAND SSD, the PCIe SSD, and this early prototype, and we just ran a bunch of workloads. I captured the QDEP1, showing about 7.3x faster on QDEP1. That's a direct latency measurement through the stack, all that. And we've done that with other OSs and demoed at various places, and it varies from OS to OS and thing. But 7, 8x, 6x in some cases. And we've demoed it up to QDEP8 because after QDEP8 you get pretty close to maxing out the buses. So it's great and real, and that was the message we tried to send here. But it says one other thing that's really important if you're paying attention. We just talked about something that's 1,000x faster, and here we demo it at 7.3 times faster. Okay, so if you were listening to this, it's like, wait a second, it's 1,000 times faster, why are you demoing it at 7.3x faster? And it is 1,000 times faster, that part's not an exaggeration. But here we're showing a demo, and my group's responsible for the controller architecture for this. So this is like my group's architecture. And it's like, we didn't screw it up either. It's not an architectural problem of the controller for this thing. It's an SSD. This is an illustration of the problem. This shows there's a problem. The storage stack, even with a bunch of stuff we've been doing, and I'll talk about some of the optimizations we've been doing, and with the new memory that's 1,000 times faster, when you run it through the storage stack and you make it into an SSD, and we didn't screw anything up, it's 7.3x faster. Okay, 7.3x is really good. I mean, if you think about block storage, 7.3x, that's not like something to ignore, not like something we'll continue to optimize and all that kind of stuff. But it says there's this huge room for persistent memory because this particular memory is 1,000 times faster. How are we going to get that 1,000 times faster? Are there applications that need 1,000 times faster? There are. But as a block storage device, it's 7.3x faster. Make sense? I mean, in other words, there are things in the storage stack that are a bottleneck, and although we're going to chip away at them, they're going to remain a bottleneck. And by the way, if this 3D crosspoint memory were infinitely fast, had 0 latency, this number would change to about 8x, less than 8x. So it's not like, well, we'll just get better storage class memory. Doesn't matter. It's all the other things, okay? So now let's dive into that a little bit. Here's a NAND SSD on NVMe. So the best bus for storage and a really good SSD, I think, if we do say so ourselves. I mean, there are other good ones too. But, and it's, since MLC and it's new technology, NAND's basically getting, for the most part, not faster. And going through the whole stack of file system, storage stack, driver, platform link, in this case NVMe, controller firmware, controller hardware, this is controller on the SSD side, and then transfer over this is within the controller transfer time, and from NAND to the buffers inside the SSD and the latency. You go, wow, that adds up quite a bit. And now you take all this time and collapse it down a lot, and you still have stuff to do error correction and stuff like that, and some mapping of things for errors and stuff, and you have some